Hello and welcome everybody. Today in geometry we are looking at something called mathematical induction. So this mathematical induction is basically a form of a proof, but it's more of an algebra proof. So it takes the idea that, well, you need to show something is true algebraically, but unfortunately, it's not as simple as just kind of plugging it in because that's not really a proof. So we are going to, try to figure out how that's going to work out in this case then, okay? All right, so here is an example of something that you have to show by mathematical induction. Now, underneath right here, you'll see that I have somewhat of an equation right here. I have 1 plus 2 plus 3 plus 4 plus ... plus n is equal to what? So just to kind of give you an idea right here, 1, well, obviously is equal to 1 if there's only one term. If I have 1 plus 2, the answer is going to be equal to 3. And if I have 1 plus 2 plus 3, the answer is going to be equal to 6. And then 1 plus 2 plus 3 plus 4 is going to be equal to 10. And then 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. Now, on the right-hand side, I'd like to know what the answer is without having to write out all the terms every single time. Because, if I have, like, say, 100 terms that I want to add, that's going to be very, very painful to try to actually add them all up. So the question is there like a faster way to see what the answer is without having to, write out every single term? So that's basically our question. So for this one, I want to show you maybe through a diagram so you can see how this actually works out. And then afterward, we'll go ahead and do like the mathematical induction proof. So if I have 1, well, that's just going to be denoted as 1 squared. If I have 1 plus 2, why don't I go ahead and denote that as 2 squares added together plus the 1 square added together. So you can see how the 1 square on top plus the 2 square on the bottom, that's the equivalent of 1 plus 2. Then if I have 1 plus 2 plus 3, then that is going to be 1 square plus the 2 squares below it, and then plus the 3 squares below it. And then the one after that, let me just go ahead and draw a few more examples. Then that is going to be 1 squared below, 2 squares below that, 3 squares below that, and then 4 squares below that. And let's just go ahead and do it for one more good measure. Let's see, 1 plus 2 squares plus 3 squares plus 4 square and then plus 5 squares. So there it is. So that's going to be kind of like the first 5 scenarios then. Now, let me kind of draw this out so you can kind of see how this actually works out, right? So here we can see that the answer is equal to 3. The answer is equal to 1 over here. The answer is equal to 6. And then the answer is equal to 10. And then the answer is equal to 15. So these are what is known as triangle numbers because when you stack them up, you can see these triangles that are being formed. Well, to be able to solve for this triangle number a lot easier, maybe what we can do is for the first one over here, for number 3 anyways, let me go ahead and draw the following. Okay, I'm going to draw something that's congruent to it, like so. So then that way you can kind of see how that actually works out. Here, it doesn't look like it's stealing too much because what I did was I just introduced something congruent to it next to it. And the area we can easily find. That's going to be 2 times 3 because it's 2 squares on the left and 3 squares on the bottom. Well, if you take 2 times 3 and then you divide it by 2 because I created 2 of these triangles, then your answer is going to be equal to 3 then. So one way to look at it is going to be 2 times 3 times 1/2 then. Now for 6, I can do exactly the same thing. I can draw something that is congruent to it right next to it like so. And if you look at it that way, then now this is going to be 3 times 4. And then if you divide by 2, because it's what I'm looking for is half of that, then that means 6, I can look at it as 3 times 4 multiplied by 1/2. With the first term, I can technically do the same thing. I can say that that's going to be 1 times 2 and then divide by half 2. So it looks like we have something working here, pretty consistent so far. Let's try for 10 over here. Maybe what you can do is draw this part out as well. So here, if I extend that out, then you can see that it's 4 times 5. And then if I half that, that's going to be my 10 then. So 4 times 5 times 1/2. And then finally for the next one, you can probably get the idea as to how this works out. I am going to extend that out. And if I do, then it looks like I have 5 squares that are going to be in the column and 6 squares that are going to be in the row. So 15 should be equivalent to 1/2 multiplied by 5 times 6. So according to this, where n, I guess in this case, represents how many terms I have, what it's equal to is going to be the following then. It's going to be equal to n multiplied by n plus 1, and then multiply by 1/2, because n times n plus 1 would then be the rectangle that I'm forming every single time, where you'll notice that the row is always going to be one more than that current term. And then I'm dividing by 2 because, well, it's half the area of that rectangle then. So that's kind of like, how you can show this visually. So that's kind of nice then. Now, unfortunately, this is a very, very specific situation where I can show you geometrically. When it comes to mathematical inductions, you might sometimes have a more complex equation, and then I can't really show it visually. So the question is, well, how do we prove this using algebra without having to, rely on drawing it out? Because, there are just times that I just can't. And that's where mathematical induction comes in, okay? So the idea of mathematical induction is the following. Mathematical induction is really just an algebraic proof. The steps are very, very simple. There are only 2 things that you need to do. Step 1, show that the anchor term works, meaning the very first term that you can plug in, show that it is going to be true for the equation. And then afterward, step 2, you're going to assume that the term n is equal to k works. And then afterwards, we need to show that n is equal to n plus 1 works. So here you can think of the mathematical induction as like a system over here, or it's kind of like it's like a machine. If I show n is equal to 1 works, what I can do then is I can take that n is equal to 1 and throw it into step 2 over here, because in step 2 right there, I'm assuming that n is equal to 1 works. Or actually, I proved that n is equal to 1 work. Then this machine will then show that n is equal to 2 is going to work. Then I'm going to throw that result back into the machine in step 2. That will show n is equal to 3 works, n is equal to 4 works, and so on and so on and so on, thus having to prove that every single term works then, okay? Rather than just plugging in values of n and showing that, yeah, it's going to be the same every single time. Nonetheless, let's go ahead and try it out so you can see what I'm actually talking about. So let's go ahead and look at the problem that we just did right there, where we have 1 plus 2 plus 3 plus 4 plus dot 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 plus n is going to be equal to 1/2 times n plus 1. And then I want to show that this is true for all the values of n's that are going to be natural numbers. So that means like counting numbers. 1, 2, 3, 4, 5, 6, and so forth, okay? So 1, 2, 3, 4, 5, and so on and so on and so on. So here we go. Step 1, okay? I want to prove that or show that n is equal to 1 is going to be valid. So that part is going to be simple because all you're doing is just letting n is equal to 1 in both sides of the equation. Now, on the left-hand side, if n is equal to 1, remember, n represents the number of terms, okay? So n is equal to the number of terms in this case. So then that means I only actually have 1 term on the left, and that's just going to be 1. On the right-hand side, I'm plugging in n is equal to 1, so 1/2 multiplied by 1 multiplied by 1 plus 1. So this, if I clean it up, 1 does equal to 1, so yeah, there you go. That shows that n is equal to 1 is going to work. Now, step 2, this is where we're going to build that machine, so then that way we can go ahead and show that all the terms afterwards will work. So the way this works is assume that the term n is equal to k is going to work. So for some arbitrary term, I'm going to assume that it works then. Okay, so that's going to be my assumption. What I need to do then is I need to show that the term n is equal to k plus 1, which is the next term, is also going to work out. So you can see how then we can just take my step 1, which is n is equal to 1, throw it into the machine, which is step 2, and that'll tell me every single term afterwards is going to work out then. All right, so let's see how that works out then. So according to my assumption, what is it that I have? Well, the given right here is basically going to be my assumption that n is equal to k works then. If n is equal to k works, then this is what I know then. 1 plus 2 plus 3 plus 4 plus dot 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 plus all the way to the kth term or the nth term, whatever you want to call it, is equal to 1 over 2 times k plus 1. So that is going to be my given because that is, again, I'm assuming that n is equal to k works. What I need to do is I need to prove that n is equal to k plus 1 works then. So I need to show that the next term actually works. So my proof is to go from here to show that 1 plus 2 plus 3 plus 4 plus dot 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 plus k plus 1. Actually here, let me just kind of like write it. Yeah, so k plus 1 is going to be equal to 1/2 multiplied by the k become k plus 1, and then the k plus 1 become k plus 2, because remember, we're showing that the next term is going to work. So that's why k becomes k plus 1, k plus 1 becomes k plus 2, and so forth. Well, there you go. That's going to be my setup right there. Okay, we're not quite done. So that's the idea still. Okay, so when we're looking at it as a proof, this is my given, and this is what I need to show or what I need to prove. Your job is to fill in all the algebra that's in between. All right, so let's take this guy right here, and I'm going to go ahead and put it down here right here, and I'm going to take this, and I'm going to put it down here also, and we're going to go ahead and fill in the void in between them. Okay, so with the given, this is what I have. I want to basically go from this step all the way to this step. Now, working on the left-hand side, working on the right-hand side, let's see. What we can do is I want to, make it match. I want to make all the terms on the left match all the term that's on the right. Now, on the left-hand side, that's the key right there. You'll notice that I have 1 plus 2 plus 3 plus 4 plus all the way to the k. Whereas what I want to get to is 1 plus 2 plus 3 plus 4 all the way to k plus 1. So here's what I'm thinking. Why don't I add the term that's missing there? Okay, why don't I add the term that's missing, and that's basically the next term. So here's what I'm suggesting then. On the left, I'm going to do the following. 1 plus 2 plus 3 plus 4 plus dot 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 plus k. I'm going to go ahead and add in the next term. So I'm going to say plus k plus 1. And right there, now that matches perfectly to what I have right there, because the previous term to this k plus 1 term is going to be k. Now, I need to balance the equation. So what that means is on the right-hand side, I am going to have to add exactly the same amount. So on the right-hand side, I am also going to add k plus 1, just as is. Okay. The left, we're not going to touch anymore because this is exactly what I want on the left, right? That is done. On the right, now you just have to show algebraically that this thing right here, what we have right here, is the same thing as what we have right there. So do a little bit of algebra work. The algebra work that I'm seeing is, hey, I'm noticing that they both have k plus 1 in common. So maybe what we can do is factor that out. So let's go ahead and factor out the k plus 1 that they have in common. So k plus 1, and then multiply by what's left if I factor that out. I have the 1/2. I have the k, and then I have the 1. Okay, so that's factoring the k plus 1 they have in common. Look at what I have. Look at what I want. I'm noticing I'm getting closer and closer to it. I have the k plus 1 multiply part out, so that's good. I don't have the 1/2, so maybe that's something I need to work on. And I also don't have the k plus 2, so that's something I need to work on as well. Well, if I want some terms, why don't I go ahead and make it a pair? Well, the one term that I'm looking at right now is the 1/2. So what I'll do next algebraically is, why don't I go ahead and take what I have and multiply out the 1/2, or actually more like factor out the 1/2, okay? So the k plus 1, I am going to leave alone. For this term right here, I'm going to take out the 1/2 because look, the answer calls for a 1/2, so I should have one out there. If I factor out the 1/2 that I have there, then the first term that's left is going to be k. 1/2 factor out of 1, well, how many 1/2s are there in 1? The answer is 2. So then all that's left is 2, and hey, look at that. That is now exactly my answer. And there you go. That's going to be your proof then. Okay? All right. So the idea is, once again, make a machine. Okay? This mathematical induction is just make a machine. First, show that the first term, the anchor term, is going to work then. And then once you do so, you're going to take that anchor term and, you're going to then create a machine where you can throw the anchor term in there. And then that machine will then show the next term will work, and the term after that will work, and over and over and over again. And that's the idea of mathematical induction then. Okay. Okay, let's try a few more of an example or see how this works out a little bit more complex. So this is an example of where I definitely cannot draw something out to see how you actually work then. Prove that this is going to be something that works also. 1 squared plus 2 squared plus 3 squared and so on all the way to n squared is equal to 1/6 times n plus 1 times 2n plus 1 for all the values of n that are going to be natural numbers. Okay, so let's go ahead and start then. Okay, start by showing the anchor works. So here for the anchor, I'm going to go ahead and show that n is equal to 1 is going to be okay because that's the smallest natural number. On the left-hand side, I see 1 squared because n is equal to 1, n is the number of terms. On the right-hand side, I am seeing 1/6 multiplied by 1 multiplied by n plus 1, which is 1 plus 1, and then multiplied by 2 times 1 plus 1. So let's go ahead and clean that up. That's 1/6 times 2 times 3. So that looks like it's 6 divided by 6. So it's equal to 1. So yay, we're happy. The anchor is usually very, very simple. So that's the good part. Now, the hard part is I need to go ahead and do the machine then. So assume that n is equal to k is going to be okay. I'm going to need to show that n is equal to k plus 1 is also going to be okay. All right, so first we'll start with the n is equal to k term to show that it works. Or sorry, I don't need to show that it works. I'm going to assume that it works. So let me just kind of write down what that means then. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus plus k squared. We are going to assume that that's equal to 1/6 multiplied by k multiplied by k plus 1 and then multiplied by 2k plus 1. Okay, so this is going to be our given because that is what we're going to be relying on. What I need to do is then I need to prove that the n is equal to k plus 1 term works. So from there, what I need to get is 1 squared plus 2 squared plus 3 squared plus 4 squared plus plus, if it helps, it's supposed to be k squared first, and then we have the k plus 1 squared term. And that is supposed to be equal to 1/6 multiplied by, remember, k gets replaced by k plus 1. So k plus 1 multiplied by k plus 2 multiplied by, in parentheses, 2 times k plus 1 plus 1. So that's what I have as a proof then. This is what I'm given. This is what I need to prove. Okay, so let's take this nasty thing. We're going to go ahead and put it on the bottom. And we're going to have to now show the work that goes from what I have on the top, go to what I have on the bottom. So just like in the previous example, I think what we need to do is look at the left-hand side, right? Notice that what I'm missing from what I have to what I need to get is basically the next term. So just like in the previous problem, what I'm going to do is I'm going to add k plus 1 squared to both sides. So on the left, we have 1 squared plus 2 squared plus 3 squared plus 4 squared plus plus k squared. And then now I'm going to add the missing term that I want, which is k plus 1 squared. And that is going to be equal to 1/6 times k plus 1 times 2k plus 1. And I'm also going to add that term to the other side to balance the equation. Okay. On the left, that is clear. That is going to be equal to what I have, so that's good. Now on the right, this is the part that you have to show algebraically to do the proof. Okay, so let's see here. I'm noticing just like before, we can probably factor out some terms. I can factor out the k plus 1 they have in common, and that's a good thing because I have a k plus 1 factor out over here. So let's see here. Let's go ahead and factor out the k plus 1 that both of these terms have in common. Here's the k plus 1, here's the k plus 1. If I factor out the k plus 1 that they all have in common, the first term, all that's left is 1/6 multiplied by k multiplied by 2k plus 1. And then plus, there's going to be a k plus 1 that's left on the right-hand side. Okay, so that part is set. Just like before also, I noticed that there's a 1/6 that is inside that I would like to have it on the outside. So maybe what I'll do is I'll go ahead and then extract out that 1/6 by factoring out from all of this nastiness over here. So we have the k plus 1 that we factored out from earlier. We have the 1/6 that I'm going to factor out. In the first term, all that's left is k times 2k plus 1. In the second part, if I'm factoring out 1/6 of k plus 1, then what I have is going to be 6 times k plus 1, because it's kind of like saying I'm working backwards. So 1 6 times 6 is equal to 1. So that's where that 6 is actually coming from. All right, taking a look at what we have and what we want. I have the k plus 1, I have the 1 6 right here and right here. So now it's just a matter of cleaning this guy up over here to show that that is the same thing as this guy. All right, so this is where your algebra skill comes in. So 1 6 times k plus 1 multiplied by, for this guy, it looks like I'm probably just going to have to multiply all that out and clean it up then. So that's 2k squared plus k, and then plus 6k, and then plus 6. Cleaning that up a little bit more. So 1 6 multiplied by k plus 1, and then multiply by 2k squared, and then plus 7k, and then plus 6. And so that right there, I do believe it should be factorable. Okay, that right there is a polynomial that's factorable. And the factor is going to be most likely going to be this guy over here. So 1 6 multiplied by k plus 1, and then multiply by, since k plus 2 is going to be in the answer, I do believe that one of the factors should be k plus 2. And what's left over here now, if I multiply backwards, k plus 2, if that's one of the factor, then the first part of it, 2k is going to be one part of it, and then plus 3, that's going to be another, because 2k times k will give you that k squared, and similarly, 2 times 3 will give you that 7. If you multiply that out, I definitely do think that it's going to work out then. And hey, look at that. Now we're getting really, really close to our answer. So 1 6 times k plus 1 times the k plus 2 that we factored out. And this part over here, well, let's go ahead and rewrite that then. How about let's write it as 2k plus 2 plus 1, because I noticed there's a plus 1 right here, so I'm going to take that out. And if you look at the 2k plus 2, well, there you go. That's going to be that part then. All right. All right, let's take a look at this one last part, and then we'll go ahead and call it. This one's going to be a lot easier. Prove that by induction that 6 to the n plus 4 is divisible by 5. So this terminology means that is divisible. Okay, so then you can divide through then. For all n, that is going to be whole numbers once again. So let's go ahead and start with the anchor. Okay, so for the anchor, I'm going to show that n is equal to 1 is going to work out. And if I have n is equal to 1, then on the left is going to say 6 to the first power plus 4. And that is going to be equal to 6 plus 4, which is equal to 10. And 10 is divisible by 5. So yeah, that checks out. So this is a little bit trickier because there's no right-hand side, but in a way it's a lot easier because there's no right-hand side. Now, let's go ahead and go for the proof then. So assume that n is equal to k is going to work. I'm going to need to show that n is equal to k plus 1 is also going to work. Okay, so let's go ahead and write that out as a given. We're going to go ahead and say that, let's see, given that 6 to the k plus 4 is divisible by 5. What I need to do then is I need to prove that 6 to the k plus 1 plus 4 is then divisible by 5. So right there, replacing k with k plus 1 once again. So let's go ahead and take this guy right there. I'm going to go ahead and, oh, I can't move it. So it looks like I need to split this up. So let me go ahead and put this down here. So prove that 6 to the k plus 1 plus 4 is divisible by 5, right? So let's go ahead and clean this up a little bit. Okay. Actually, wait, I'm kind of, you know what? This is actually kind of strange because I actually should have this on top, and I'll show you why in just a little bit. So if I want to show that this is going to be divisible by 5, here, this time around, we're going to go ahead and work backwards in a way. Because, you know, when it comes to proof, so long as you work from it forward or backward, then it's fine. Just so long as you don't work in between, then you're okay. So let's take a look at what we have. 6 to the k plus 1. Okay, 6 to the k plus 1. What I can do is the following then. I can take this guy and write it as this. 6 to the k, and then multiply by 6, and then plus 4. Right? 6 to the k times 6 and then plus 4 because of the exponential rule where you can take the exponent and split it up. So here I'm just taking 6 to the k plus 1 and writing as 6 to the k times 6 to the 1. And that's where that 6 is actually coming from. Okay. Now, Looking at what I have right there, I don't know if that's divisible by 5. But what I do want to know, know is that this guy right here is divisible by 5. So the best thing I can do is, hey, let's go ahead and make that a pair. Let's go ahead and make that 6 to the k plus 4 a pair. And here is the key to how to do it right there. 6 to the k times 6. If there are 6 of these terms because it's multiplied by 6, then here's what I can do. I can extract out 6 to the k, one of those terms out of the 6. And then we have the plus 4 right there. And if I take out one of the term, well, that means that there are going to be 5 of those terms that are left. Okay, so note here, if I add these two together, that's still going to be equal to 6 to the k times 6, because 5 apples plus 1 apple is going to be equal to 6 apples. And that right there is going to be our key, because this guy right there, this is going to be divisible by 5 because of the given. And this guy right here, I definitely know is also going to be divisible by 5 because there is a 5 that is there. So right there, that's going to be your proof. Very, very simple, right? Well, there you go. Thank you so much for watching. And hopefully, you know, it is somewhat thing that you can use or learn from them. All right, I will see you guys later. Bye-bye.